Hey guys, I'm back to show you another example relevant to section 7.5 on defective matrices here. There's a couple of different scenarios that can happen, and I just wanted to give you another example to show you this. I'll try to keep it short. In this example that I'm about to show you, here's my matrix. One of the things I want to point out here is this matrix doesn't have a lot of zeros in it, which means that your calculation of the determinant is kind of a pain. Well, in a case like that, it won't be uncommon for somebody to just tell you what the lambdas are, right? So that you don't have to spend that time and possibly make a mistake with the characteristic equation and all of that kind of thing. So I'm just going to tell you right here what the lambdas are. The lambda equals -2 shows up 3 times. Okay, so the same eigenvalue 3 times. Now, let's take a look at the corresponding eigenvectors and see what we get. I have to add 2 to the main diagonal of this matrix. So if I do that, I'm going to get something like that, right? And I'm going to cross off the bottom row because it turns out to be the same as the top row. And then I'm going to let me just do a quick ERO here. I'm going to add 2 times the first row to the second row in order to get a 0 here. Of course, this is going to be 0. What you can see right away is there's only one free variable, right? Only one free variable. And I would call that z equal to t. Based on the second row, y and z have to be negatives of each other. So y would equal -t. And then from the first row, x and y have to be negatives of each other. So x is equal to t. So I'm only going to get one vector here, one eigenvector. After I bust out the t out of that, this is my eigenvector. So this is like a seriously defective matrix, right? It's become pretty badly defective. So I'm only going to get one easy solution to this system, which is e to the -2t times 1, -1, 1. Okay, so we got that one. We got that one. But we have to come up with 2 more solutions. Okay, so I did this kind of quickly in class at the end, so I just want to be sure that I go through this so in a way you can understand this. Remember that we have, on my previous video, we showed this little diagram. You know, you're basically trying to create new solutions using these W's. Okay, so, you're choosing a W1. Remember this? We choose W1 so that after you multiply it by A minus lambda I, you'll get W2, which is not 0 yet. In fact, what this will be is an eigenvector. But then when you apply A minus lambda I a second time, the second time it does become 0, okay? And using that then, you create this second solution, which is e to the lambda t times W1 plus t times W2. Right, so that's what you're going to do there. But then, to get a third solution, it gets even more complicated. You actually have to create yet another set of vectors here. So I'm going to draw my picture again, and this time we're going to use W3, W4, and W5. So this is kind of how you can draw this picture. Okay? And it's a similar picture. You basically want to choose your W3. You want to choose W3 so that it will survive A minus lambda I the first time and the second time, but not the third time. Okay, so the W5 is going to be an eigenvector. And if you can do that, and I'm going to show you how to do that in a second, if you can choose this W3 strategically so that it survives twice, but not the third time, then you can get a solution here, which would be e to the lambda t times W3 plus t times W4 plus, if you remember, it was t squared over 2 times W5. I did not derive that in class, okay? That's something that isn't that hard to do, but you have to like plug in a trial solution into the original differential equation. I guess I didn't write, this is our usual problem we're solving. if you plug this trial solution in on both the left side and the right side, you can come up with this, with these coefficients, and you'll understand why there's a 2 on the bottom and all of that. I don't need you to get too concerned about that. That's not really the purpose of what we're doing here. But I do want you to be able to construct this solution. Okay. Now, I drew these diagrams kind of above each other on purpose, because the idea here is if I do this job first, which is what I really need for W3, or for X3, if I do this job first and I choose W3 and I find W4 and W5, then I actually can then choose W1 and W2 to just be whatever W4 and W5 come out to be. In other words, I'm allowed to reuse those same vectors. So that's kind of cool. So let's go through this. I'm going to, I need to calculate A minus lambda I, right? Which in this case would be A plus 2I. And of course, that's going to be this matrix right here. So let me just write that down. 1, 1, 0, negative 2, negative 1, 1, and 1, 1, 0. By the way, be sure that you work with A plus 2I and not the row-reduced version of it. You have to stay with the original matrix when you're doing the calculations here in this diagram. Okay? Now, A plus 2I squared, I have to square this matrix out. I'm going to spare you that detail because it's easy to do and no need for me to take a huge amount of your time. But you have to square this thing, and what you're going to get is the following matrix. Negative 1, 0, 1, 1, 0, negative 1, and negative 1, 0, 1. Okay? So that's what you're going to get. And you are also going to need to cube this matrix this time because you're going to apply A minus lambda I 3 times, right? It turns out, though, that when you cube this matrix, you're going to get all zeros. Okay. So you can check all that out. You can just do the calculations, but that's what's going to happen. Okay. So I need to choose W3. I'm going to work on this bottom hopscotch thing here first. I need to choose W3 so that it's going to survive 2 powers of A minus lambda I, which means it's going to survive this matrix, but not survive this matrix. Well, not surviving this matrix is automatic, right? Nothing is going to survive this matrix. So I'm just looking for a vector that will survive this matrix, and whatever it is, I'm going to call it W3. And again, I want to make it simple, and a very simple choice again. Okay, I mean, I know it feels like we can always seem to get away with this. It's not always true. But 1, 0, 0 is going to work great. Because when I apply 1, 0, 0 to this matrix, I'm going to get the first column here, which means it's not 0. It hasn't been killed by the second power of the matrix. Okay, so then I can go back and I say, all right, W3 is 1, 0, 0. What is W4? Well, I just have to find how do I find W4? I take W3, whatever I chose over there, and I multiply A minus lambda I, which is this matrix, by W3. And if you take this matrix times W3, you're just going to pick off the first column of the matrix A plus 2I. So you're going to get that. Okay? And then W5, as I have already explained, is just going to be the first column of this matrix, which is negative 1, 1, negative 1. And again, this one is an actual eigenvector. Notice that it's just a multiple of the eigenvector we found over here, right? So this is just a multiple of that. So I can actually already write down the rest of my solutions, because I'm just going to, notice my correspondence here, I'm just going to make this W1 and this one W2 as well. Okay, so that it works in the top diagram also. Okay? So here we go. X2 of t is going to be e to the negative 2t times W1, which is the same as W4. Oops, that's a minus 2 and a 1. Plus t times W5, which is negative 1, 1, negative 1. Just like that. There it is. And the third solution is just e to the negative 2t times W1, which is 1, 0, 0, plus t times W2, which is, I'm sorry, this is W3. W3 is 1, 0, 0, plus t times W4, which is that vector, plus 1/2 t squared times W5, which is that vector. Okay? So here you go, you've got x1, x2, and x3, right? So now I can go ahead and I'll erase these calculations now. I can write down my final answer. It's actually gone fairly quickly. Final answer, x of t equals c1 times the first solution, which we found earlier. 1, 1. Good. Plus c2 times the second solution, right there, which is e to the negative 2t times 1, negative 2, 1, plus t times negative 1, 1, negative 1, plus c3 e to the negative 2t times 1, 0, 0, plus t times 1, negative 2, 1, plus 1/2 t squared times negative 1, 1, negative 1. And that would be the final answer. Okay? I hope these diagrams make sense. You're really just multiplying, as you hop to the right, you're just multiplying by a minus lambda I, and you're trying to choose vectors that survive a certain number of hops, but not that many hops. So in the case of W3, it needs to survive twice so that you can get 2 more terms here in this last solution, but then eventually has to die. And of course, W1 is only supposed to survive 2 hops. So if I choose it to be the same as W4, we know that W4 survives 2 hops. So W1 is also going to survive 2 hops if we make it the same as W4. Okay, so that's a handy way to do this that doesn't take a whole lot of effort. Really, the worst part of it is you just have to like square and cube out, a minus lambda I. It takes a little bit of time to multiply those matrices out. But once you've done that, you're really in pretty good shape. Again, let me know if you have any questions on either this clip or the one that I made, the other one with the mixed eigenvalue case. Hopefully, if you just practice this a little bit, you're going to find it's pretty computationally driven. It's not terribly theoretical. You just have to get the process down. Okay? All right. Thanks, guys. Appreciate your attention on that.